Perfect. So now we're all live. And so what we usually do is do sort of just a quick round. And everyone gets a chance to sort of say what they've been up to and what they're interested in, if they've got any questions or sort of longer discussion items. And so actually maybe today we could start off with the new faces in the crowd. And if you want to just kind of share what you're interested in sort of connecting on, what you'll be working on, and sort of yeah, how SimPEG is used in your work and how you might want to contribute down the line. So Jaja, would you like to kick us off?
Yeah, sure. Hi, everyone. I'm Jaja Sun. So I'm currently an assistant professor at University of Houston. I did my PhD degree at Colorado School of Mines with Yogo. So currently, I'm working with my graduate students, mostly on joint inversion. So that is my biggest interest and also the focus of my research here at U of H. So both Xiaolong and Xinyan are my PhD students. They are working on joint inversion. But we want to do more than just joint inversion. We want to extend geophysical inversion to the construction of 3D quasi-geology model. So basically, we want to go from geophysics and to all the way to do the inversions, interpretation, classification, and all the way to our final product that shows a 3D spatial distribution of geological units. So that's the big focus of our work. And we have been using SimPEG. We have benefited so much from SimPEG, both Xinyan, Xiaolong, Jay, who already graduated, and also Kenneth. He's another of my master students. We're all using SimPEG. So thank you so much for this such a wonderful tool framework upon which we can build our work. It's greatly accelerated our work and also make our work much more reproducible. So we are here because we have developed some joint inversion codes, and so I think we have tested in quite a few datasets. So I think we maybe we wanted to see how we can contribute our piece of code to SimPEG. Also, of course, at the same time, we want to learn more about SimPEG. So that's all from me. Thank you. Yeah.
Excellent. Thanks, Jaja. And correct me if I mispronounce your names. Xiaolong or Xian, would either of you like to jump in and sort of add, or if both of you are willing to, just a bit of what you're working on and maybe how you're using something?
Yeah, sure. So I can go first. My name is Xin Yan. I'm working with Dr. Jia Sun. I'm also using SimPEG, and one of our colleagues, Kim, he already developed a part of the coupling method, which is cross gradient into the SimPEG. So I'm using his coupling term to do a lot of tests. Right now I'm doing the synthetic modeling to do the joint inversions. Also using the mixed LP norm. I'm using L12 norm a lot to do the joint inversions. Current stage, I'm testing the synthetic modeling, different model pairs, different model scenarios to test the recoverability of the physical property relationships based on the scatter plot of the inverted values. The next stage, we hope to apply this method along with SimPEG into the field data. Specifically, it's in the Canada, the Quest project, using the airborne magnetic data and also the gravity data set to do the joint mixed L12 norm inversions.
Thank you.
Thank you.
Hi. Hi, my name is Xiaolong Wei from University of Houston. I'm a PhD student working with Dr. Jia Sun. So the scope of my research is joint inversion and uncertainty analysis. So currently I do the joint inversion and analyze uncertainties in the deterministic framework. And in the future, maybe start from the next year, I'd like to implement joint inversion and analyze uncertainty in the basin framework. So I benefit a lot from the SimPEG. Actually, I'm familiar with the name of each guys here because I always check the source code and see the contributors. And I'm glad to be here and hope I can do some in-kind contributions to the SimPEG in the future. Thank you.
Mike.
Unmuted. So I guess I'm just starting to get back into SimPEG stuff after a little hiatus here. I just started a new project with the U.S. Geological Survey, and hopefully going to be using MT gravity and maybe some passive seismic data.
We're having a bit of trouble hearing you.
Oh, really? Is that any better?
Yeah, that
No?
is better. It is better.
That's better?
Yeah.
Yeah.
Okay. I don't know what I changed, but so I guess I just started a new position with the U.S. Geological Survey, and we're going to be using MT gravity and some passive seismic data to try to study a volcanic field kind of at the north end of the Napa Valley here in California. So we'll start out, I guess, with individual inversions of each of those data sets, and then if things are going well, maybe we can play around with some joint inversion stuff as well. So I'm happy to be back, have my fingers back in this stuff. That'll be good.
Perfect. Okay. I guess before we move on to everyone else, does any folks who are sort of rejoining or first joining, do you have any specific questions or things that you want to talk about today? Or just sort of tune in and then we can bring questions next time. No? Okay, that's fine. Then let's start around the room, and if folks want to provide updates and maybe just a bit of context of what you're working on too for all the new phases. So I see Joe's got some notes in there. You want to kick us off?
Sure. As I was playing around this last week with stuff, I noticed that NumPy is switching their document, like the way it looks when you go to it, like the documentation page. They're updating it to this PyData Sphinx theme. Like the written style is still the same. I posted about it in Slack really quick, but the theme looks really nice and clean. I'll share a little bit of it here really quick so you can see what the PyData Sphinx theme looks like. But it's just really clean website layout as far as how it formats the documentation when you're looking at it. As opposed to what we have now. It's a theme that seems to be used from the PyData community, which is a big open source community focusing on using Python for data science and stuff. So I think it'd probably be a good thing that they're trying to, push people to provide a common interface, I guess. So it could be a good thing, and I think we should use it.
So Joe, PyData is what? Is a new data format, or is it?
No, it's just a community.
Or community?
Yeah, I started looking into it a lot more. Lindsay, do you know much about the PyData community?
So it's basically, like, in a sense, a collection of like projects and developers who work broadly under the umbrella of data science. And so projects like NumPy, SciPy, scikit-learn, matplotlib all sort of fall under the PyData umbrella. I don't know if there's like an official project listing, but there's also then sort of like community meetups and things like that. So I don't know if you've ever seen sort of like there's Python meetups and those sorts of things, but there are also PyData meetups. And those are basically sort of generally people who are doing broadly defined sort of data science within the Python ecosystem.
Yeah. But it seems like a very nice community, and it's like the theme looks really nice. That's got me excited.
And Joe, they also have, or I think, because Pandas, I think, were the ones who maybe kicked this off. I think that they've also maybe given some guidance as to what the top level headings should be. Is that true? Of like gallery, user guide, API?
I can go back and check on it, but yeah, it is definitely Pandas who've been spearheading it. And if the PyData theme documentation has a lot of information, I believe. But I haven't looked into too far as much of what they recommend. Like, oh, these should be the high-level things. It seems pretty common format of, okay, there's a, getting started, a user guide, API, release notes, that kind of thing.
Excellent. How much of a lift do you think it'll be to move over to that?
I haven't tested it out yet, but it should just be switching a theme in the file, in the configure file.
Yeah.
So right now it uses some Sphinx theme.
To read the docs, yeah.
Yeah, the read the docs theme. So it should just be able to switch that around. I haven't tested it too much out yet.
One thing to look at further is that those themes sometimes don't support some features. Like for instance, I got stuck on trying to put the embed Plotly stuff in our pages, and it would only work on Alabaster, those kind of things, right? But I don't think we were doing anything too fancy with SimPEG, are we? Except the tiles, I think it's pretty straightforward.
I mean, we can test it out, but it's a much cleaner interface and looks much more, 2020 instead of like 2010, 2005, something like that. Let's see what else was I gonna say. I put up a PR on GeoAnna about that adds the kernel functions that we've used in the SimPEG EM1D to that, as well as it also adds a really, really simple, just layered EM layered EM solution. So it's actually using the kernel inside SimPEG or inside GeoAnna. So it's not just like a useless thing sitting inside there for something else to use. Just a really simple function, and then it tests against the Warden-Homan solutions. I was gonna ask. I was gonna ask him about the EMPyMod and filters and stuff, because I can't figure out how to get the EMPyMod solutions to match with the theoretical stuff from Warden-Homan. I'm not quite sure why. Like I've got the Warden-Homan stuff implemented. I copied most of it over from what was before and double checked some things on the components. I think there's a little bit of a sign off on a couple of them. But all the components now check out XYZ for everything. It's testing against that for a half-space solution for each source orientation and receiver components. So it's the way I did it in there is a general you get XYZ components out at each receiver location for an arbitrary source direction. So it's testing all that. Passed the test. I just want to I do need to double check that the orientation sign convention is proper, consistent with what we expect it to be with SimPEG. Obviously, the Z component is not too much of an issue because, okay, it's polarized in whatever direction the dipole is polarized, right? But I feel like, okay, maybe the Z component from the X polarization might be backwards or something, possibly. So we need to, that's why I was hoping to double check it with something external to the Warden-Homan, because their coordinate system is, Z down, Z positive down.
Then would it be better to test with the PDE code rather than EMPyMod? Because we don't know EMPyMod and SimPEG is consistent.
Yeah, we can probably test it. I'll test it with the SimPEG code just to double check, and if we get the the sign conventions right with that compared to the layered solution, then I'll feel much more comfortable. Because it's like all I'm concerned about is whether it's got the right sign of the. I'm not necessarily concerned about its accuracy at that point. I just want to double check that it's got the right sign.
Well, I mean, when I was working on the 1D stuff, I was quite cognizant of that. So whatever I've done in there so far is deliberate, and I believe the signs are correct. I mean, if you want to double check, I'm totally happy with it because. What were you doing to double check it before? Did you test it against SimPEG stuff, or did you just? No, I mostly just use my hands, right? Okay. You figure out, okay, like I've got a vertically oriented magnetic dipole. Okay, the currents are going this way. This is my convention. So I did it that way. Okay. And it all matched up. So by all means, do a numerical test. But I'm pretty sure they're right. Okay. Oh, good.
I wouldn't be like 100% confident in things that are associated with signs. I think there were, I I seem to recollect that there were one or two places within Warden-Homan that maybe signs were not right. So I think Sagi's suggestion is perfect. Let's just go with something that's entirely different. Do a numerical solution, put out a vertical dipole or whatever, and just check it out. That's the cleanest way.
And there's quite a few places in the 1D code also can go wrong, because especially like time domain, like transform, then depends upon what your waveform is. The same, like the sign could change, and then
I wasn't even concerned.
I think it's it's worthwhile to check.
Yeah, I was just the only part I put in there was a finite or a frequency domain one, so I wasn't concerned about the waveform at that point. I was just okay. Well, let's do a frequency domain one and double check. So
I'll do that.
When
I was playing around with stuff, I had done quite a few tests with just like grounded source transmitters. And I had compared like some quasi-analytic solutions with both SimPEG and with the E3D, the UEC E3D.
Yeah.
And I think
I'm sure it's right now. I'm sure that they're matching each other for each of the the half space solution from Warden-Homan is matching with the the layered solution. In all the cases that I have right now, I just want to double check that their signs are right. I've gotten, so anyway, the faster kernel functions are on there, as well as the faster derivatives. The way I implemented it was there's a NumPy version of the same function, and it's tested against that the NumPy and the Python C++ thing produce the exact same result. It's just the way it works is that, okay, you would have to specifically tell it to build those external libraries before you ever call the setup, the Python setup file. That way we could still distribute the source code on pip, and people can just pip install it without worrying anything about it. It'd still be a pure Python code. And actually at this point, those two, I rewrote it in NumPy, and essentially it's the same speed as the Python C++ one that I wrote. But obviously it uses more memory to do that. That's why I left it. It's comparable speed to the NumPy one right now.
That's cool.
Oh wow, that's pretty cool. Huh.
Yeah. Then.
But Joe, it's actually that's even faster than the previous Fortran code, right?
It's about it's on the same order of magnitude, yeah.
But you mentioned the sensitivity calculation was actually faster.
Oh yeah, the sensitivity calculation is much faster. It's able to calculate the sensitivity with respect to the susceptibility, the conductivity, and the thicknesses all at the same time for the cost of about 2 forward models.
That's interesting, because it means vectorization in NumPy sort of enough to replace lower level code. Is that the kind of conclusion we have?
Generally what happens. The vectorization in NumPy is very fast. You just have to be able to take advantage of it properly.
Right.
You can take a look at that. You'll see what it does. I've gotten discretized testing up on Azure DevOps using Azure pipelines. So we have a unified place to test discretize on Windows, Mac, and the Linux kernel. And then it's also deployed from Azure pipelines as a separate stage. So the way that the testing works is first stage, it does for a PR, essentially it would test everything, but it wouldn't deploy anything like normal. And then when it gets merged into master and tagged, it'll test everything. And then if it all tests and it's a tagged release, then it'll do the extra steps of building the source code, distribution, uploading the documentation, and building Windows wheels for each 3.6, 3.7, 3.8.
Wow, that's amazing. Whoa.
And I had it, right now I set it to build Windows wheels against the normal Python installation, not Anaconda, because we can do that and build it against, that should be handled by Conda Forge essentially. Is there anything else I had in the notes there? Oh,
The testing problem.
yeah, I found out where it's going wrong on the SimPEG EM tests. But I still don't know why. I'm still trying to double check on how to fix it. It's a really weird memory problem that's happening inside a function in GeoAnna that should never, like, there's no reason for it to happen. All of the matrices, I don't know what's going on with it.
Is there a way?
It's happening on a NumPy dot, it's happening on a NumPy matrix times another NumPy matrix transpose. That's all that's happening. And both those matrices are like created from other NumPy routines. And it's really annoying. But at least I know where the problem is.
Nice work, Joe. That, like, the line that you sent me was just, I have no idea how on earth you found that.
Well, I had to I figured out how to get to SSH into the Travis machine. So I did that, and then I started like going in and editing it, you know, on a terminal and figuring out, okay, well, what's going wrong? Where's it going wrong?
Nicely done. Very nicely done. For your PR on GeoAnna, what do you need for that? Do you want folks to test some things, review? What would you like from the group here?
I don't know, just, I guess you can look it over if you want to give it a once over. I'll double check on there's a few things I need to double check. Is that one, that the source code that's distributed to PyPy when it gets uploaded contains everything, including the Python files.
Cool. So Joe, to make sure that the Python version or C version of that kernel function, what I basically need to do, I install GeoAnna first, or clone GeoAnna. What do I need to do? Install the C version of the kernel?
You basically just set an environment variable, and it's detailed in there. And that'll tell it to include the Python and source files. I'm pretty sure I'll be able to have the Conda Forge installation do it automatically.
That'll be great. But basically, it is changing a certain variable in the setup.py, and then basically running the Python.
It's an environment variable. The setup.py file checks for an environment variable to conditionally add an extension kernel, an extension module.
Okay, got it.
Thanks, Joe. Any other? All right, thank you. Cool, Devin, you've got some notes in there.
Yeah, so I think maybe the first thing, kind of most important, is there's a PR hanging out there for improved stability of the mag problem. There is something with the Travis test that seems to be failing on the frequency domain EM. I'm noticing in all the PRs. But basically, this one for mag has been vetted, it's been approved, but it's going to fail on something completely unrelated to what's being added. So kind of hoping that this issue can get addressed so we can bring it in.
Did you check for the gradiometry what Joe asked, Deb? Did you check if the same problem happened on the graph on the GG?
Oh, magnetic gradiometry?
No, the gravity gradiometry. It has the same kernel as the mag code, so that's why I was asking.
Oh, I didn't check out the gravity gradiometry. I just did grav, so I can look into that again. But that would
be good, yeah. Do it all at once, right? Because it's going to be the same issue. Okay.
No, I'll do that test. So I guess there is one more thing that I could do, but yeah, I'd like to go and investigate why that FDEM test is failing.
That's what I was talking about earlier. Like, I figured out where it's failing. I'm still trying to figure out exactly how to make sure it doesn't in the future.
All right. Well, then I'll get to the gravity gradiometry stuff today, just so we can finish it off. And if you wouldn't mind throwing some energy at the FDEM thing, then we can just get this finished, because I like completing things. It's almost at the finish line. The other stuff.
The error happens in like a call to some GeoAnna function. So the error is happening inside GeoAnna, but there's still no reason it should be.
Okay.
So I changed the function a little bit in GeoAnna to see if it makes a difference, but I don't know.
All right. Well, maybe we'll talk and kind of try and track down that issue. I mean, if it's something that's like a one-liner or something super simple, we could probably just add it in this PR.
Oh,
but
I can show you. I'll write the exact line that it's failing on. It's in GeoAnna. If you go to, I'll provide a link to it right here.
Sure.
Thanks, Joe.
We'll talk about it later, but I'll send a link and you guys are like, why is it going to fail on that line?
Okay, so moving on to the next thing, was working on the spontaneous potential. So we have tests that match that to an analytic, and we have the adjoint tests passing for the current, current source and the current density source. So for sources defined by Q and as JS. So we now have like this more or less a good suite of tests for SP, I think just using a tensor mesh. Now I need to start looking in, can we easily add octree mesh capability for this? And then I think there's some validity to having maybe putting in the 2D solution or get the 2.5D solution, which I don't think we have implemented yet. What do you think, Sagi?
I was thinking about that, but I wasn't sure.
One of the problems I remember is that there's like you have a dam that's leaking. Yes. And that maybe that has like enough of a 2D geometry for you to sort of treat the problem that way.
I problem to think about a little bit more, because so 2.5D, why we're doing that is you got a point source, right? But if you think about the SP, it's not a point source, right? So
yeah.
It's I wasn't sure that's needed. So
yeah, it's true, because then you're sort of assuming that there's like a crack that runs horizontal if you're
like in the dam example, I basically used the 3D code and just switched the 2D to a 2D mesh. So what's assuming you got an infinitely long line source in the strike direction.
Yeah,
I thought that's fine, but I am not 100% sure that's the case.
Well, I guess that type of problem, you want to know up, down, but you also want to know horizontally where that leak might be. So
yes, I wasn't sure like using a 2.5D is like a sort of relevant use for that.
Yeah, but we should definitely implement the octree capability.
Yeah, that requires a few other things. So setting up that boundary condition is not implemented in the octree, but I think Joe got most of the pieces. So all we need to have is like ability to grab the boundary faces and the boundary cells and stuff. I think we've already got that function.
Yeah, we have those utilities. Yeah.
Yeah, so it shouldn't be hard. I mean, it's supposed to be straightforward.
Yeah, so I mean, if that's not too challenging and I have the pieces to do it, then I'll try and implement that and validate it with the tests that we have. And then kind of one of the final things would be then to just come up with a couple of good tutorial examples for maybe the forward problem and the inverse problem. So progress is being made on the SP stuff. And the last thing that I've been working on is with the DCIP. So I don't have it all up now, but last week I've been running kind of these validations of our code against other coding packages. And UBC has a DCIP octree code that the electric potential is discretized at cell centers, and it uses kind of like a primary secondary approach. So you're using an analytic solution to give yourself the electric potential, and then you use a discretized operator to get your right-hand side, and then you put in your actual conductivity model. You'll solve that system to get the solution that you want. So the way that they've implemented it seems to do very well, and I've noticed that there's maybe some questions we have with how we are discretizing our source term and potentially interpolation, and whether or not something's being different. So I'm kind of looking at the way that SimPEG is solving this problem, either with the electric potential on nodes and at cell centers, looking at how it's creating the right-hand side, and just kind of playing around with that to figure out what's best. So as of right now, if you're putting the sources at arbitrary locations and the receivers at arbitrary locations, and you simulate the half-space response, you're going to get some errors they're not massive, but depending on your cell size, I think we can do better, and I think we should do better. So I've just been playing around with that. So
what do you mean, like okay? Is that, do you have some sort of like a percentage?
Yeah, I'd say maybe like 10% error. And I'm just trying to figure out what's the biggest source of it. So one thing I played around with, at least for SimPEG, the nodal formulation does better. And I've tried playing around with some things to take the source term and discretize it at the nodes. And so I think right now it does a very basic averaging to adjacent nodes. So you're somewhere in the cell, and then it just averages very rudimentary to the nodes. And I've started playing around with kind of a weighting it so it's the 1 over the distance or 1 over the distance squared, and got a little bit of improvement. Now I'm wondering if the interpolation matrix from the nodes to the receivers is being done differently in that Fortran code. So I still have to do some tests where I'm putting electrodes on a specific locations and really trying to investigate what's happening at each step. But I mean, as of right now, I had a mesh that I thought was pretty reasonable, and the UBC code will give me errors that are maybe 1% or 2% compared to an analytic solution, and SimPEG right now is more like that 5 to 10. But it'll be really, really great if you put everything on the nodes exactly, or everything on the cell centers. But for arbitrary locations, I'm noticing some errors that I'd like to reduce.
So if you put, let's say in the nodal formulation, if you put the source and receiver exactly at the nodes, are you getting about that similar error, like 1 to 2%?
Yeah, so these are the tests that I'm just about to go and do. Right now, I'm just doing it in comparison to the manual example that we used for DCIP Octree, so the UBC code. So that sort of motivated this, but now we actually get to, okay, let's do this for real. Let's really figure out where the differences are, and really make a good test and start to dive into it. But I think it would be pretty useful.
And one thing, kind of just to be fair, would be nice to test for the layered solution, Dev, because what the UBC code does, actually, that half-space solution, and force the simulation to be like that, at least for the half-space.
Yeah.
You're going to get absolutely good,
it's true. The half-space, you're going to go forwards, and then you're just going to go back again. Yeah.
Yeah, so what I would, at least put a layer in it, and then do the test and see if, so we could do a 3 simulation UBC code, 1D solution and the SimPEG solution and see how the error looked like. That would be great.
Yeah, with a 1D model.
Yeah.
We do have a 1D code. So.
We do.
Which will eventually get Geo in.
So that's about it for me. I think I've kind of, Joe and I maybe at some point in the future we'll continue on the documentation for discretize, but these are sort of the three things I've been working on.
Devin, one more thing about the DCIP octree stuff. Just keep in mind that there's some assumptions being made when they create the right-hand side that didn't work at all when I was trying to do my underground simulations.
Yeah, right now this is for a surface survey, and as I recall, once you voice those concerns, we fixed them, recompiled, and have released a new version of that code.
Really? Because I remember talking to Roman about it, and he didn't really have a good idea on how. So I still am not convinced that DC octree code is going to work for kind of an underground situation where you have a tunnel and stuff like that. So
Mike, I think you need to speak closer to your microphone. I think that's the problem why you're cutting out.
Yeah. So the latest release of DCIP octree was on July the 8th of 2020. So that would be a new release based on, I think, the issues that you noticed and perhaps the sensitivity weighting. Actually, that was the big ad, was the sensitivity weighting for DCIP octree.
Could be. I just remember that when I had talked with Roman at the time when I was having the problems, he didn't really know how to fix it, and he didn't seem like there was a lot of impetus to fix it either. So I didn't know that he was planning on doing that or not. So just keep. I don't need to do anything. Just keep that in mind that there may be a limitation there. You may run into some weird things.
Well, I think you might be right. I can actually bring it up.
Let's maybe move on from this, Deb, if that's okay. We've got about 15 minutes left.
Yeah, sure.
That's maybe one we can regroup on next time if we need to.
Okay.
Cool. Thank you. All right, John, I see you've got some notes in there.
Yeah. I got the derivatives passing for the resistivity and the phase. Yeah, but that's now the adjoint, and yeah, I'm at a loss. I've tried everything. I've pulled that apart, reformulated it, and I don't know. It's just not passing. Like they're on the same order of magnitude, like what comes out of it, but yeah, I don't know. I've tried. Yeah, I don't know. I need some material or something to be looking at to point how this was done, I guess, in the first place, just like the impedance. Like I see how it was formed, but it's like, where did this come from, and how can I use this idea? Because it just having to break the derivative into the real and the imaginary.
So
sorry.
Have you are you testing on the actual MT problem, or you've made a separate code to test that amplitude and phase?
I'm using the test. I'm using an MT problem that I made up, and then I'm also just using the test one under tests as well.
Okay.
Yeah, and both of them are giving me the same thing. It's like, it looks like it's almost there, and it runs, and it's like all the matrices are the right sizes, but yeah, the values just aren't. Yeah, it's not.
You will you're welcome to the 2 world. So you will love to see the number 2, and then you will really appreciate the comment coming out of that test when you got 2.
Oh, I like the ones that it doesn't pass as well. But yeah, the comments are pretty good. But yeah, the adjoint. So I don't know. I might have to bug someone to help me take another look at it. I haven't pushed what I recently did. Like I really broke it down, but yeah, still nothing. But I might have to bug somebody. And
I'm happy to jump in and take a look. We can think through this together. Adjoints can be such a pain. So
yeah, I think it's just I'm missing like the whole idea of adjoint. Like I'm just not too familiar with how that is formulated. So yeah, maybe something like that will help. But yeah, And then after that, I think, yeah, we need the 2.5D solution. I'd really like to work on that. And if someone could point me at would it just be Warden-Holman? Should I look in there and start, or like, I heard there was talk about the boundary condition versions, or maybe not doing a primary second.
Like, there's no 2.5D in MT, it's 2D.
Oh,
so
sorry.
You don't have to do 2.5D. I actually played a little bit. I can share my notebook later. Yeah, so yeah, it's a pure 2D problem.
Yeah, because the 3D it's just, I've been doing some 2D and 3D, but it's just to get the domain large enough, for a 2D problem, it's just taking a little bit too long. And yeah, I think the 3D problem isn't going to be too accessible until we get this like tiled version kind of going, and then we can invert over multiple frequencies, because it's just taken a long time to invert. And compared to some of these other codes, like they've figured out how to do this fast. So there's maybe go from 2D, and then yeah, the 3D we'll start doing we'll go right into the tiling over frequencies and see how that works.
Yeah, that's great. I think I have a little bit of write-up and example code that I wrote. I haven't tested yet, but I can point to that. It seems like you got pretty big motivation to develop, so that's great.
Yeah, we just got into we were starting to get a couple jobs, and what was working before, of course, when you test everything before, it's working, and then once you put it into production, it's all falling apart. So yeah, so definitely I can put some time into this, and I need to get back to the DC tiling problem. So we'll just, after I'm done this MT adjoint stuff, I'll just go in and do DC and frequency, or DC and MT into the tiling, try to tackle them at the same time. And that's what it.
Thanks, Sean. Yeah, well, we can definitely iterate on the adjoint, and having a 2D solution, I think, will be super useful. I don't know if you watched, so on MTNet, there's now a series of webinars.
Yeah, I missed the first.
Yeah, but they're recorded, which is great. So if you do want to catch up on it afterwards, they're now up on YouTube.
Oh, awesome. Cool.
Yeah, but so Martin Unsworth gave the first talk, and it did sort of underscore to me that, you know, having a 2D code would be really valuable, because he showed, you know, results where they did both 2D and 3D inversions. And it's just nice to be able to compare and, you know, see that you're getting similar structures, and builds a little more faith in your results and things like that. So,
yeah. Agreed.
Excellent. Thanks, John. Dom.
Elbow deep in Dask again, learning. I thought I knew what I was doing, and then turns out that I don't. But I think I'm getting closer. Just learning how to deal with futures, right? Passing futures and scattering data and all that stuff. But I think I'm getting closer. And yeah, that's about it. That's it.
Fair enough. Excellent. If you do have like notebooks as you learn stuff, or like even code snippets you want to share around, I'm sure that would be useful, but also no pressure if you're still sort of in the figuring things out phase. Cool. Sagi.
I have nothing really particular in these days for development, but I just want to appreciate what Joe did. So I'm mostly using in these days, and so Joe's efficient improvement will make a huge improvement on my end, because I'm running lots of airborne inversion, and as well as Joe implemented this sensitivity for thickness, as well as the susceptibility. So that kind of gives us another ability to have more inversions. Like we can put the susceptibility in when we're inverting for, or you can invert for both the resistivity and the thickness value. So you could do, like, let's say 5 layers and then try to find thickness and resistivity values. So that would be really nice. And one thing, and kind of connected to that, we just submitted the proposal here back in Central Valley, basically flying over entire California. And we're not sure whether we're going to win or not. But if we win, we're going to use SimPEG extensively to the entire airborne data set. And a few things, we suggest a few things about handling the magnetic data, as well as the 3D effects. So yeah, we're going to further develop the 3D simulation code that can handle large scale data. And in terms of magnetic data, it's usually just ignored. And one thing that I was thinking, kind of having a similar functionality like a BPMG. So we still use the 3D tensor code or whatever octave code, but have an ability to parameterize that as a layer and invert for a thickness as well as the value. That would be quite relevant for a lot of hydrogeologic application here. So yeah, actually, I was actually curious about BPMG. Is that kind of supports both the gravity and magnetic data and MVI to do a layered inversion? Basically, is that what it does?
Not MVI. They're computing the secondary field, so they can do like the self demag, but not full vector.
Yeah.
What do you have in mind for layer though? Because VPMG is not actually dealing with layers, right? They're just prisms that are shifting up or down. Or do you want to parameterize it, or?
But I think I would do a similar sort of idea of like, so tensor, it's actually simple. You got a tensor mesh and you got a 2D plane, and each cell has a number of layers. So you can parameterize that as a layering, but we can put some sort of smooth constraint at each point of the layer, top and bottom. So it's a kind of similar idea in the airborne code, but we use the 3D mesh to parameterize that.
Soggy, didn't you do that at one point?
Yeah, I was going to say, yeah.
I did. So I actually got the mapping function, but I think at that point I used the DC code to do it, and then, but yeah, it's basically done. But I want to. This is better kind of application. So what we're interested in this thin sort of lava flow in California. And that's like, it's called Lovejoy basalt, and it is actually randomly magnetized. So you can see this random signal on just looking at the data, but it'll be nice to map out that thin layer and as well as the random direction. And I think it could make a pretty big impact on their hydrogeologic interpretation. So yeah, that's a detail, but that's sort of where I'm going and mostly use.
So the importance of that is just to basically try to find like the thickness of this lava layer, because that is either going to, I mean, just because how that interacts then with the groundwater hydrology, or why is the lava layer important?
I think that in general, this there is like a volcanic debris flow. It's not a permeable pathway. So okay. What's the hard part is like just using resistivity, you have no chance to distinguish that. But if you have another data set that can kind of distinguish this sort of like a lava flow or whatever volcanic material, that kind of gives you an idea, oh, where's like this boundary, impermeable boundary that can block your hydrogeologic pathway. Anyway,
wow. That's an interesting problem.
Yeah, lots of interesting problem here. Anyway.
The bottleneck with those methods is always just to generate your 3D, like your model, right? Go from a surface. If it's layers, it's not so bad. But if things are complicated, you know, if it's non-convex layers, I mean that's always the tough part to start. But maybe GeoSci can help you.
So you're
no, but if you've got a single interface and you represent that as some kind of variable sinusoidal spline function, that should be quite doable.
Yeah, one layer is fine. I mean, it's just if you're folded or faulted or whatever, that makes the problem more complicated, and yeah. It's a big area, then you need to model the whole California, then you end up in
one thing I'd probably stop, but one thing nice about that layered inversion, like for each pixel, you got different permeability, like a magnetic permeability value. So I'm not inverting for a single value for entire layer, but you got lots of value. So within the layer, it can change, it can vary. So even if you got a complicated structure, but the assumption is suppose you got general layering where the lava flow happened. And then I want to sort of like see that kind of variation within that layer. anyway, so that's where I'm going.
That's a cool problem, Sagi. Thibaut, would you like to go next?
Yeah, I will go fast. It's like almost 11:30, but yeah, I've made good progress with merging my PGI framework with master at the moment. So what I'm trying to, I'm able to rerun most of my example, but I'm running obviously in a Travis issue at the moment. And also I had a lot of things on my branch, so I'm trying to pass out all the things that I've changed that are not related to PGI in particular. So I've created like a bunch of small pull requests that will be also maybe also like easier to merge and might also help in fixing the Travis problems later on the main PGI branch. So hopefully we can move forward with that quickly. Like Joe already helped me a bit with some stuff, but yeah, I'm trying to also reduce like the PR to only what I know works well and remove all the like experimental stuff that I tried at some point that that just clutters the code, but that will still be like a fairly big PR. So yeah, I will need some help and reviewers of the code for that, and some help with the Travis. Trying also
well, we have a whole new
and tutorial.
Yeah, have a whole new SimPEG community that's in Houston and interested in geologic inversion. So there might be some input down from the new members. Jaja, that was your cue.
Yeah, sorry, I was muted. Yeah, so right now what we do with after inversion is done is that we cross-plot the inverted values. At this point, mostly in 2D, because in 3D, if you want to do cluster classification, it's a little bit more tricky, more complicated. So Jay's work and Xiaolong's work and also Xinyan's work are mostly concentrated on 2D, just two properties, mag, grab mag. And then what we do is that we write a very small piece of code, Python code, that allows you to draw a polygon. And then all the points within that polygon can be mapped into 3D. Then we look at the spatial distribution of the selected points in spatial domain and compare that with known geology. So that's how we do it. But I always wondering if there's a better way of doing that, because right now it's mostly manually select a polygon and you do so it's many iterations of trials and errors, because at the beginning you probably don't know how to cut again, partly because we use smoothness inversion. There's a lot of scattering, so you see a lot of the overlapping between the different units, and especially around the background region where you have the density around zero, cerebral around zero, you have a lot of black dots there, right? So next step would be to see if some kind of unsupervised machine learning, maybe Gaussian mixture models, self-organizing map, or maybe clustering can help automate that. And with the help of the awesome inversion algorithm developed by Dom, MixLP. Right now we are focusing on L12 because we found that L12, that's Xinyan's work, most current work, is that we found that in all the 7 or 6 scenarios we tested, L12 norm inversion, joint inversion always produce the best physical properties with much less amount of scattering. So you can recover the linear features pretty clean, much cleaner and well separated. So that allows us with the cleaner features in the cross plot, that allows the further classification, the subsequent stage of classification task much easier. Is that right, Xinyan? Do you want to comment on that?
Yes, I do have a figure. Can I show it?
Sure.
Oh,
yeah.
Okay. This is actually a PowerPoint that I'm gonna use for the sheriff lecture. I haven't finished it yet. But the figure that Dr. Sun are just talking about, I think it's this figure over here. So we simulated 6 different model pairs with different depth range and also different values. So the true model properties scatter plot are in the last column over here. And we did separate inversions in both L2 norm and also the mixed L1-2 norm. And also we did the joint inversions as well. So we put all the inverted results scatter plot together. And in comparison with the true scatter plot, we can say that the L1-2 norm joint inversion can give us the best recovered model values in comparison with the true scatter plot. So all the linear features are very much differentiated from each other, even though some of the anomalous object is very deep and has very small susceptibility values. But with the help of the L1-2 norm joint inversion, we can still differentiate the 2 linear features that cannot be differentiable in the L2 norm, either separate inversion or joint inversion.
So joint inversion.
Yeah, that's.
Go ahead.
Oh, I was just going to say that looks really nice. I think my earlier comment was that Thibaut was sitting at a place where he's putting up the PGI inversions, trying to put some pull requests and get people to review it and pass it. And you've got a whole Houston group here that is kind of working on the same kind of problem, but in a different way. So you actually have some mutual goal here to kind of work together and to perhaps develop the codes within SimPEG and ultimately maybe even result in a joint collaboration here where we look at different techniques for doing geologic inversion or quasi-geologic, getting out quasi-geologic models. So just kind of saying that I think this is kind of one of those ideal opportunities. You've got 2 different groups of people working on the same problem. Everybody's trying to use SimPEG. It's a nice format on which to kind of work together and try to develop something.
Yeah, sure, definitely, sure, agree. So Thibaut, maybe you can we can talk about later on about the pull that PR later on with more details.
Sure.
Yeah.
Saki, did you have a question there or a comment?
No, not particularly. I was curious about that. What is the connection in between physical properties? Is that the cross gradient or fuzzy mean or what's?
So right now we just purely focus on structure-based cross gradient. Yeah.
Got it. Yeah.
So that's just so that goes back to the comment Doc just made earlier on. I think so. Right now we are just focusing on structure-based joint inversion, and Thibaut focusing on the petrophysics PGI. So I think our work just perfectly complementary with each other. So yeah. So I would like to work with Thibaut. Our group would like to work with Thibaut later on. Sorry, give me 1 second.
Excellent. Thank you. Thibaut, did you have anything else you wanted to share? Was that a wrap?
Yeah, no, that's a wrap. Like there might things in the PR that we can discuss, but it's not important. Like it's not urgent or very important at the moment. Especially like I want to improve the beta estimate directive, but people that are interested are actually included a notebook in the PR to show the problem. It's just that just to give it like in very quickly that with the beta estimate right now we're doing like this ray-like quotient and we're doing 1 iteration. But actually, when you do 1 iteration, you know the order of magnitude of the ratio, right? Like I ran the test and I ran that 1 iteration thing like several times, and basically the range of beta value you can get from that by rerunning it is like it covers 5 order of magnitudes, but it still misses the real ratio by 2 order of magnitude. So it's basically a random number generator at the moment. So I propose to like basically like do. So I basically propose that we can have an option to choose a number of iterations of the Rayleigh quotient ratio we want to do. And that actually just doing 3 give you in the ballpark. So it's not that much of computational cost to get like a proper ratio estimation. So, and also that's also makes the directive like compliant with joint inversion and with like many different form of functions. So I think that's one that's would be good to have like looked at and and merge, but we might have to look through because like for a lot of example where people have like choose the right beta 0 ratio to have the example work, we might have to revisit that. Yeah, that's about it.
Cool. Thanks, Thibaut. Dieter, hello.
Hello. Yes, I learned today that Canada switched back winter time 1 week later than Europe, apparently. So here I am. Yeah, not much. Our joint paper is out. Well, it's not out. That's not true. It's submitted, so it's out to be read. Not peer reviewed, but for anyone, I think you have it in the note, right, Lindsay?
I put the archive link in there. Yes.
Yeah. Other than that, I'm currently working on automating the meshing, like frequency dependent, so that the joint inversion framework can throw any model at it and it will create the appropriate computational meshes, but give back the gradients or the model of the inversion mesh. So kind of make that a bit easier for people like in the joint inversion framework. Most of them are either used to seismics or gravity and not really to EM. So it's kind of a hard task to do a meshing. And yeah, I'm a bit on that. And I think we discussed on that previously as well, because it's not an easy task and there are more possible traps than solutions, I think. But yeah. I hope to get in something soon because I have some students that are gonna play around with different automatic and adaptive meshing routines, which are a lot are out there, but one has to look what is appropriate for CSEM or other functions. So yeah, that's it for the moment.
Doug,
and I saw, but I can have Joe a chat once. I saw that he's working on the Joanna 1D layer, so we might have a chat there once. That looks really cool.
Doug, did you have any updates you want to share?
No, not particularly. I just want to say that, Judge, I'm just so pleased that you and your students are joining this, and I hope that we can see you, on a regular basis. I think there's just so many things that we actually have in common as far as goals, both scientifically as well as numerically, and yeah, it would just be really fun to have you guys as regular participants.
Oh, you're still muted, Jaja.
Yeah, sorry. Yeah, thank you, Doc. We are very glad to be here. To have to keep our connection with all you and all you guys, the SimPEG team, and we hope that we can contribute to the SimPEG, and it's a really, really great tool. We want to promote the use of SimPEG in our community. As I mentioned, it just greatly accelerated my group's research and make it much more reproducible. So my career has been boosted by SimPEG in many ways. So yeah, we'll be here on a regular basis.
That's a quote for the website.
Yeah, just what I was thinking.
Excellent. Well, thanks everyone. I don't have any really concrete updates other than the paper that wanted to share, and so feel free to take a look. It's in review right now, so we can also sort of, if you see things that we should improve, we can take the informal review comments too. Yeah, other than that, thanks everyone. One thing that I think want to think about maybe a bit, and I'll try and get some thoughts together maybe by next week, is I mentioned sort of thinking through a bit of sort of SimPEG governance and what kind of things do we want to have in place for that? What kind of questions do we need to sort of be able to answer as a community? So if you have thoughts on that, we can maybe start to kick off that conversation a bit too. Yeah, other than that, thanks everyone. Have a good afternoon. And welcome again, Jaja and team, and Mike. It's great to
Thank you. Take care, everyone. See you next.
Hey, everyone.
Yeah.
Yeah.